Our next speaker this morning is Chad Kruger with Washington State University. Chad is director of WSU's Center for Sustaining Agricultural Natural Resources, overseeing research and extension in organic cropping systems, biologically intensive ag, climate-friendly farming, and small farms. And he's been leading their award-winning climate-friendly farming project. I didn't realize that was going to be a tongue twister. This morning, Chad is going to talk with us about building markets for biofertilizers, perceptions, and performance.
Okay, thank you. First of all, I'm feeling really good this morning because about an hour and a half ago I got an email from one of my faculty members who happens to be in Kabul, Afghanistan this week, saying that he was safe in spite of the insurgent attacks on Sunday. 48 hours of not hearing isn't a good thing. Okay, so what I'm going to try to do here today is essentially talk mostly on the perception side with a little bit of data, preliminary data from some performance around certain organic amendments being used in agriculture to illustrate that. I think a lot of people know all the big issues that we're facing, and I'm going to very quickly use a couple titles here to frame this in the sense of not so much the materials discard management, but one of the potential end uses for those materials, that being agriculture as inputs to agriculture. So Paul Roberts, a friend of mine, has written a couple books. I mean, the first one's probably over 10 years old, of oil, which when he was writing that and I was talking with him, he basically said, you know, does this mean the end of food? And so he went and wrote the book, The End of Food. A couple others, a University of Washington professor, David Montgomery, wrote this book, Dirt, the Erosion of Civilizations, which is pretty profound. And then Anna Lepay, who's the daughter of Francis Moore Lepay, who wrote Diet for a Small Planet many years ago, recently wrote this book, Diet for a Hot Planet, in terms of climate change in agriculture and food and what are we dealing with. And so there's a paper from Nature a couple of years ago that started looking at some of these big questions and how they're interacting with the planet. And we kind of adapted that for this slide, specifically looking at what are the issues related to agriculture that are big environmental issues that we need to be able to deal with. Fossil fuel energy, nitrogen fertilizer in the environment, climate change, and chemical pollution, which is the authors from Nature basically said we're not even capable of quantifying the impacts of chemical pollution. Just it's this thing out there that we really don't understand. I'm going to shift a little bit now to speak specifically to the agricultural issues that we're dealing with as a context for thinking about organic materials. And this is a story pretty traditional from around the world. There's a few examples that are counter to this, but essentially this is the trend that we've looked at for the past 150 years in our region, much longer than that in most of the other regions of the world, is basically the act of producing food itself is harmful to the soil. So by tilling, by taking a lot of the biomass that we produce in the land base of the countryside and shipping it to the urban centers where we all live, and then not shipping something back, we've essentially are pulling carbon out of the soil. We're mining carbon from our soils and putting it in our landfills and in our waterways and in the atmosphere. And this is a set of soils that are pretty traditional Palouse soils near Pullman. At basically 58, 73, and 26% reductions in carbon in these soils over the last 100 years just from farming it. And while we like to blame a lot of that on the farmer in terms of the tillage practices, the truth is, and most of it, is because we've shifted to the cities. When we lose that carbon out of the system, we also lose the fertility of the system. And this is modeled data compared with the historical data at the Pendleton sites in terms of soil nitrogen levels. And you can see that as we've produced that food and shipped it to the cities, we've lost the nitrogen out of that system too. This kind of goes back to that Montgomery book about dirt, the erosion of civilization. If we don't stop and reverse these trends, we're actually looking at something probably far more serious than drying up oil wells and things like that. So where is it going? Well, one thing that a lot of people don't realize when you talk about the carbon cycle and the carbon budget is how much of the carbon is actually in the soils and in the vegetation as opposed to in the atmosphere or even in the fossil fuels. So half as much carbon is in the soils and vegetation as in the total carbon pool of the fossil fuels. And then when we look at what that looks like on an annual basis in terms of the budget, we can see that, yeah, fossil fuels really is the current source for where we're putting emissions into the atmosphere, but changing land use and other land-based degradation is a very significant one still, and a good portion of the carbon that's up in the atmosphere up until about 10 years ago actually came from our soils and vegetation. So it goes back to that slide I showed in terms of losing it out of the soils. A lot of the carbon that's up in the atmosphere that's currently a problem is actually from our soils. The other thing that is kind of a concern here is while we know our emissions are still going up, our sinks, primarily vegetation and soils and oceans, are starting to show indications that they're not working as well as they once did. So we're losing the capacity to absorb carbon from the atmosphere through our natural mechanisms. Going to the nitrogen side just really quickly, you can see what nitrogen does when it gets where we don't want it. And nitrogen is leaky. Of 100 pounds of nitrogen applied in a field, somewhere around 4 to 5 pounds of that ends up in the food on your plate. The other 94 to 96 pounds actually ends up somewhere in the environment. And it doesn't generally end up in places where we want it. Another one that we're starting to think a lot about is phosphorus. We don't lose phosphorus like we lose nitrogen in terms of its leakiness. However, we're using it, and where it gets to, we don't really want it either. And this is basically looking at global phosphorus production relative to global demand, and we're probably looking at the potential that there won't be enough phosphorus reserves, traditional phosphorus reserves, to continue producing food to feed the planet. So if we're going to talk about things like producing biofuels or other materials, we have to be looking at these nutrient sources. Now, the good thing about phosphorus is we don't use it up like we do nitrogen. We just need to keep it where we want it and keep it cycling back in the system. So kind of to wrap up that context and really start to think about how do we look at materials that can come back into agriculture, a really smart guy says we got to think a little differently. So we started thinking a little differently almost 10 years ago now. Craig did this report, the Washington Biomass Inventory, some really quick things on it. The focus was on fuel production, could be a lot of CO2 reduction, but I'm going to give you a little bit different view of that right now, and that is not talking about energy recovery at all, just talking about if we could recycle some of that material back into our agricultural soils, what would that mean? And essentially, if we could get 20% of that carbon from the waste material cycled back into soils on an annual basis, that'd be about 10% of the state of Washington's net CO2 emissions. And the other one, the one that's almost even more exciting to me, is this green line here is the amount of nitrogen fertilizers used by Washington farmers relative to the amount that's in those waste materials. So while the discards may be a very small percentage of the emissions and everything from the actual materials management, it could literally be huge in terms of the input to the industry that's largely dependent on synthetic nitrogen fertilizer. So how do we do that? And this current generation soil amendments is a lot of what everybody in this room works on. Very good stuff that we worked on. We've done a lot of research over the years at WSU, and Craig Kruger, who's here, has done a lot of this in terms of how do we recycle these materials back into agriculture and use them for those benefits. And they're good because they recover carbon, recover nitrogen, other nutrients, they stimulate microbial activity, they improve soil health and tilth. But they have some limitations, and I think what we're coming to understand is they do have limitations. So what are the likely uses? Construction, residential, commercial, organic farms that can't use nitrogen from synthetic sources, And then, but if we really want to look, what does the marketplace look like? You know, once we expand to that, how do we get it into the mainstream agriculture? We run into an issue, and that's basically a value proposition and a risk proposition. The value proposition is most of our farmers don't make enough money on their extensive production system to justify paying very much for the inputs. You know, the nitrogen fertilizer prices have tripled over the last few years. That's put a lot of farmers under a lot of pressure. Even those tripled fertilizer prices are still a lot less than the value of nitrogen from a lot of organic materials. Starting to get closer. So basically, you're looking at essentially cereal grains and maybe some forage crops as the likely destination for these kinds of products outside of these special uses like organic production systems that really need them. And part of the issue is they're inconsistent. Hard to predict, hard to understand how to use them. They do different things every time. And so if we're going to resolve that and tap more of that potential marketplace, we got to get better at consistency and prediction. The other real key here is you look at these two grain crops, and nitrogen fertilizer is a good portion of the cost. It's material that has a lot of nitrogen, has some other benefits. If you can get that price into a reasonable place, you're going to be able to sell it. And here's a compelling point of view. There is a lot of compost being used in the Columbia Basin now, much more so than even 4 or 5 years ago. There was one company that basically said 100,000 tons going like that. The catch is it's all coming from manure from the Columbia Basin, and it's being applied to the field, total cost at $10 a ton. So if you're producing and wanting to sell it for more than $10 a ton and you're not going to get it to the field, you're going to have a little issue. So how do we do that? Well, one way to do that is rather than looking at farmers as a purely market-driven effect, let's look at, boosting a little bit more of the cost to society to actually move these materials back. So we produce wheat, which is a high-quality product that's turned into bread to be shipped to the city. And then we want to produce basically a low-value commodity and ship it back. We need to figure out how to do that. Maybe one way is to get people to actually pay a little bit more to ship back what they're purchasing and drawing to the city. Or, I'll get to that later. Another thing, going back to the slide on terms of the loss of carbon out of the soils, we know that these materials are critical to increasing carbon sequestration in soils, which puts it back also as basically the strategy to increase the sustainability of soil management from agriculture. And a couple of preliminary data slides here, we basically looked at manure from anaerobic digestion and non-anaerobic digestion compared to inorganic fertilizers to see what strategy actually is going to do the best from a greenhouse gas mitigation standpoint. And there's a couple of things to learn here. In the inorganic system, there is a little bit of soil organic carbon that's built up in that system, and this is all under irrigation. And essentially the reason there is because by providing nutrients, we're actually growing a crop which provides some carbon back into the system. You can see from both the raw manure and the digested manure that we put a lot of carbon back into the system. So relative to inorganic fertilizer, the potential is great. We also have this thing below the line, and what that is it's the nitrous oxide emissions associated with using fertilizer. So inorganic fertilizer has a fairly negative nitrous oxide emission, but manure is worse, whether it's digested or not. And what ultimately comes out is essentially that offsets the value of carbon from a global greenhouse gas standpoint. So we got to figure out if we're going to use this strategy, especially if we're going to use it as a greenhouse gas mitigation strategy, we have to reduce the amount of N2O coming off this system. This slide on the right basically is showing that there is potential over the long term to actually make a truly climate friendly or a carbon sink based system if we can figure this out. So on a 12-year time frame, we actually build carbon in the soils and have a net positive balance of carbon in this system with the manure and the digested manure. But over a 30-year time frame, that nitrous oxide starts to wipe that benefit out. So if we can deal with the nitrous oxide, we really could have a net positive greenhouse gas situation. This next slide is another way to look at the potential of these organic amendments in terms of restoring carbon to soils. And what I've done here I probably should never have done. And Craig and Sally did part of this research and published it. And then Claudio Stockel and our group did another part. And what I did is I took two completely separate types of studies and put them together so that you could see them together. One was actual experimental data. The other was modeled based on physical principles. And I put them together, and like I said, I shouldn't have done that, but you can see how stunning this is. So GP17 is a site in Douglas County. It's a winter wheat fallow system where there's no organic amendment and then 3 rates of biosolids applications. The Linn no-till lower and upper is the range of potential carbon sequestration from no-till applied in a winter wheat summer fallow system, in a really dry system, and the Pullman no-till lower and upper is the range of carbon sequestration in a really wet wheat production system in our region. So this right here, my cursor will work, this is what everybody's talking about when they talk about no-till carbon sequestration as a strategy for global greenhouse gas mitigation. And it is. It's net positive in terms of the sense that it puts more carbon in the soil. However, when you compare it to what happens when you put biosolids or other kinds of organic amendments in the soil, there's no comparison. If we want a strategy that's actually going to do something about greenhouse gas mitigation using our soils, it's going to come from organic management. So there you go. Does that make you happy, Sam? All right, good. The N2O emissions from those low rainfall systems are pretty low anyway because there isn't a lot of nitrogen in the system. So looking at, and we've got modeled slides too, I didn't put them up, but it is a pretty consistent story. So looking at the next generation, where do we have to go unless we're going to figure out a way to pay for this, either publicly funded or some other kind of mechanism that's going to bridge that gap past that $10 a ton applied? We need to look at something else. Plus we need to look at what's a bigger marketplace where the ag producer is actually going to be willing to pay a lot more, or potentially a lot more, to get a product. And so we've got a couple things here. Number one, it's got to be consistent, it's got to be reliable, it's got to be predictable, and we have to be able to apply it precisely and know what's going to happen every time. If you can't meet that standard, you're going to have a really hard time tapping these higher value marketplaces because there's other factors that are more important. So for instance, if you can't say you'll get nitrogen from this material on this day, it'll get used up and it won't be there, you're not going to sell to an apple producer because they have to have the nitrogen shut off in the system, literally like a switch, at certain points in time, or their fruit quality goes down. Once fruit quality goes down, they can't sell the apple. So if you want to get into these kinds of higher value markets, potatoes, seed crops, sweet cherries, raspberries, greenhouse and nursery crops, you got to have something predictable and reliable and something you know exactly what it's going to do. The potential is great because these people can pay for it. These people can pay for it, they're interested in it, and they're interested in it because they have the same issues going on that you see in those polluted soils. Over the last 40 to 50 years of managing these soils intensively to produce high quality fruits and vegetables, they've seen their soil quality diminish, and it's starting to affect things like yield and fruit quality. So there's a lot of research going on now in terms of looking at things like even like antioxidants that are saying basically if we don't do something different with our soils, our fruit quality is going to diminish, and that's going to hit them in the marketplace. So there's a lot of new interest just in the last 12 to 36 months around looking at the potential for organic amendments, even in conventional systems, as a grand strategy for sustainability and health in the production of fruits and vegetables conventionally. And we can do some of this, and we're going to have to do more and more of this. So Craig's going to talk about the nutrient recovery work that we've been doing a lot more, but I'm going to use a phrase that they're using in the biofuels market. They say drop-in biofuels, drop-in fertilizers. That's what we've got to be looking at. We have to be looking at products that can come from organic sources that a conventional producer can say, that looks, acts, and essentially is the same as what I already use. I'm going to take that material and essentially substitute the conventional synthetic or phosphorus mined fertilizer or other petrochemical that I'm using currently. And there's a lot of this. I showed you the slide that says we have enough nitrogen in our organic materials to supply our needs. Just from the dairies in Washington State, less than half of them is 20% and 27% of the nitrogen and phosphorus demands in our state. So we can do this if we go about it. And Craig will talk more about our fertilizer recovery process, which we're piloting with manure, but they're going to work on it with municipal solid waste as well. That's what the products look like. That ammonium sulfate solution is essentially a traditional product. And then I'm going to close with one last thing, and this is kind of the holy grail kind of product idea. And obviously Brassica seed meals are made from Brassica crops. So if we're thinking about biofuel production on the diesel fuel side, a lot of people are talking about canola and mustards and camelina and this kind of thing. There's a meal that's left over. Those meals are quite interesting because they have some phytotoxicity issues, and that's a bad thing if you're using it wrong. It's a good thing in other cases. How do we actually make use of both the carbon and the nutrient values in these meals, as well as the phytotoxicity value? And essentially, this is a big challenge to sequence how to make the product work every time. And there's hundreds of varieties, therefore there's hundreds of potential products. Hundreds of soil situations, cropping situations. All of these issues have to be kind of systematized so that we can make a product that essentially works like Roundup. And we've been doing some work on this, and it shows a lot of promise. There's a lot of other potential really interesting chemicals that could essentially come out of the organic waste stream and substitute for the kinds of chemistries that we use in agriculture that would be an organically derived material, which is safer, and that's part of the reason that we're looking at this. But I'm going to give you a final caution on all of these materials and use the Brassica seed meal as an example of what the issue here is. So Mark Mazzola at the Tree Fruit Center, he's USDA, has worked with these materials looking at apple replant disease. Can this help give us an option to deal with root lesion nematode when traditionally the only option has been fumigation? We're trying to eliminate fumigation, and EPA keeps cracking down and reducing the amount of fumigants that we can use. Well, here's 2 years worth of data. Basically what this is this is the control, this is the fumigant, and this is the Brassica seed meal. Same trial, same place, 2 different years, 2 different results. And Mark actually thinks this is pretty good results, and I do too, but the catch is it's not the same quality as the traditional fumigant yet. And so in order to get a producer to buy into this, especially if they're producing, apple, or if they're trying to reestablish an apple orchard at $30,000 an acre, or if they're trying to produce a potato crop where if you have one nematode in your load, you get rejected at the processor. You can't have this kind of inconsistency yet. So we have more work to do on this kind of thing. And what we probably will ultimately get to is some mix of a biological with a traditional fumigant as the strategy. But the potential is great. The toxicity reductions are great. And all of this is very valuable and worth doing. However, what's happening right now is our producers are looking for this, but they're a risk-averse community because they can't afford to have a $30,000 per acre investment die. They can't afford to lose their $3,500 acre potato crop. So if you're going to sell something into that marketplace, don't overstate it. And that's what's happening a lot right now, is basically everybody's promising the moon with each product, and what happens is it comes in, somebody uses it, it fails, gets rejected, that word is out in the ag industry, and it's done. And so you got to be really careful. There's a lot of promise in these materials, but there's a lot of potential for failure too. So, thank you.
Thank you.